Hey guys, welcome to chapter 16. In this chapter, we're going to talk about something called electrochemistry. So this is where we're going to beautifully tie together electricity and chemistry by studying the flow of electrons. So what is electricity, and certainly what form are we going to study as chemists? So electricity is just simply the flow of electrons. Electrons, as you know, are negatively charged particles, right? So they're going to flow from their place of negativity to a place of positivity. So electrons flow from negative to positive. Those moving electrons can produce light and heat. And so we are going to look at that as we study this idea of electricity. So what we see in this picture here is how we as chemists study electricity. So we're going to study it through something called redox equations or redox reactions. So that stands for oxidation reduction. So we're going to look at how electrons flow from reactants to products. So just a quick overview of electricity. So we probably haven't ever looked at it or thought about it from a chemistry standpoint. So let's just take a big, broad overview of what electricity is. So electricity, like we said, is the flow of electrons. So electricity, places that we probably have come into contact with it, lightning, definitely a flow of electricity. Batteries, so batteries we talk about a lot with electricity. So let's think about these different scenarios, right? So lightning, what causes that? Well, there's a positive charge that kind of accumulates at the top of a cloud where like near the ice and stuff. There's going to be a negative charge that accumulates at the bottom of the cloud, right? And if there's a large enough difference between those two, what we'll see is it creates this little like channel for the electrons to transfer from the negative charge, right? So it kind of acts like a conductive wire, neutralizing that difference in charge. If there is a large enough separation and they're close enough, the clouds get close enough to the Earth, there's a bit of positive charge associated with like ground. So we'll see that cloud to ground lightning, same thing, just like a little channel for those electrons to transfer. If the clouds are not low enough or the charge isn't great enough, we'll see the lightning kind of scatter throughout the cloud as opposed to cloud to ground lightning. In the battery, we see the same thing. So we see kind of a collection of positivity up here, collection of negativity down here. And we will connect some sort of conductive wire between those two, which will allow the flow of electrons, causing the electricity to also flow through that channel. So all of this boils down to electrons are flowing. Okay. So how do we as chemists study the flow of electrons? How do we study how electrons are moving? We do it through something called a redox reaction. Redox is just shorthand for oxidation reduction. So a redox equation is just a reaction that causes electrons to flow. So where do we get this oxidation reduction or redox term from? So there's going to be two scenarios that are going on. There will always be a reduction on one side of the reaction arrow. There will always be an oxidation on the other side of the reaction arrow. So these happen together. You cannot have one without the other, right? Sometimes the reduction's a reactant, sometimes the reduction's a product, so it doesn't have to be in this order. But if you have one, you must have the other. So how do we know what the reduction is? How do we know what the oxidation is? Electrons, we're going to track the movement. So in an oxidation, that's where we lose electrons. So if we lose electrons, that's the oxidation. What do you suspect the reduction is? Yeah, it's a gaining of electrons, right? So somebody's going to lose electrons, somebody's going to gain electrons, and that's going to create that flow. Flows from one place to the other. So how do we know who loses? How do we know who gains? Well, there's going to be a list of rules that we follow that have to do with oxidation numbers, okay? So what we're going to build in this chapter is we're going to first look at the rules for assigning oxidation states, right? And then once we are proficient at assigning oxidation states, we can then look at, well, what was the oxidation state in the reactant? What was the oxidation state in the product? And how did that change? Did it lose electrons? Did it gain electrons? So first we have to identify states, then we can identify changes or transfers. So here's our rules for assigning oxidation states. This list or this rule is a hierarchy. So rules at the top of the list trump any of the rules at the bottom of the list. So it is a hierarchy list. As we move our way down, those rules are less important. So the first rule is the oxidation state of an atom in a free element is 0. So if we have something like iron, Fe, metal in a reaction, that's going to have an oxidation state of 0. If we have something, so iron, oh, not up there, iron would have an oxidation state of 0. If we have something like a diatomic, so oxygen or nitrogen that exists as O2N2, that oxidation state would also be 0. So free atom or free element oxidation state will be 0. Oxidation state of a monoatomic ion is equal to its charge. So if we see a metal that it's charged, so let's say iron with a 3+, the oxidation number or oxidation state for that metal will be a 3. If we see a sodium with a 1+, that would be a 1. If we see fluorine with a 1-, that would be a -1. So whatever the charge is on that ion, that's going to be its oxidation state or its oxidation number. The oxidation states for molecules. So now we're not talking about free elements anymore. We're talking about something in a molecule. The molecule has to equal 0. The sum of the charges or of the oxidation states has to be 0. So something like NaCl, that's a molecule, right? When I add the oxidation state of sodium plus the oxidation state of chlorine, it has to be a neutral 0. Okay, that means one of them is going to be positive and one of them is going to be negative. Kind of an addition or extension of that rule, if the molecule has a charge, so if it's a polyatomic ion, now when I add the oxidation states of nitrogen and oxygen, the sum of those would have to be -1. Okay, so if it's a neutral molecule, the sum of the states is 0. If it's a charged molecule, the sum of the states is that charge. The next rule is going to be metals. So as we're working our way down this list, metals are more important than nonmetals. So metals will always have a positive oxidation state. And quite often it just mirrors what their charge would be as an ion. So the metals will always have a positive, and very often it's identical to their charge if they became an ion. Non-metals. Our non-metals are the least important of the assigning of oxidation states. And the non-metals have their own kind of chart. It didn't fit on this slide, so I've given it a new slide. But the non-metals will assign according to the following chart. So this chart is also a hierarchy list. So as we move our way down, fluorine trumps group 5A. So we would assign fluorine first, then just kind of give 5A whatever's left. So fluorine, if that's an option, that will always be a -1. Hydrogen, if that's an option, that will be a +1. Quite often, oxygen is a -2. And then the group 7, 6, 5 just follows their charges. So let's look at some examples. I've given you this kind of list of rules, and you're like, great, what am I going to do with that list of rules? So what we're going to do with these is we're going to try to predict the oxidation state or oxidation number. I keep saying state and number. When I learned it as the oxidation number. Your textbook is now calling it oxidation state. Both of those are the exact same thing. They mean the same thing. So let's take a look at some examples here. So I'm going to do this first one with you. So we're going to try to determine what is the oxidation state or number for sulfur. What is the oxidation state or number for oxygen? So we're going to go down our list of hierarchy rules. So the oxidation state of a free atom is 0. Well, neither of those are free. They're in a molecule, so that is not important to us. The oxidation state of a monoatomic ion. Well, again, we don't have an ion, so that's not important. The sum of the oxidation state in a neutral molecule is 0. So this is going to be something very, very important to us. As we start assigning oxidation states, the sum of sulfur and the 2 oxygens has to be 0. Metals, we don't have a metal. We have 2 nonmetals. So now let's go to our chart. We still haven't assigned an oxidation state. We know that it has to be neutral, but let's work down our chart. So no fluorine, no hydrogen, oxygen. Finally, we've come to something. So the oxidation state for oxygen is going to be a -2. So oxygen has an oxidation state of -2. And now we have to assign the oxidation state for sulfur. So each of the oxygens is a -2. There's 2 oxygens. So total to the table, this part of the molecule brings a -4, right? Each of the oxygens is a -2, and there's 2 of them. So now that we have assigned the oxidation state for oxygen, now we go back to this rule. Sulfur has to have an oxidation state of whatever to make this neutral, to make the sum of the states neutral. So that tells me that sulfur has to be a +4. So sulfur has an oxidation state of +4. Oxygen has an oxidation state of -2. But when we add all of that together, it's a sum of 0. So let's do another example together. Let's do this one. So let me clear all the ink off of this slide. So we're going to go through for this one. Oxidation state of a free element is 0. We don't have any free. Oxidation state of monoatomic ion. We don't have any monoatomic ions. Sum of the oxidation states. So we got to make sure that potassium plus oxygen equals 0. Metals have a positive. So in this case, the potassium trumps the oxygen. So I'm going to assign the oxidation state for potassium first. If we look at a periodic table, potassium is a group 1 metal. So when he becomes an ion, his charge is +1, and his oxidation state is going to mirror that. So potassium is a +1. Now I see that there's 2 potassium, so 2 total to the table. This guy brings a +2. I have oxygen now. Oxygen needs to be whatever to make sure that this molecule is neutral. When I add them together, it equals 0. That's the most important rule. So that tells me that oxygen in this case has to be a -1. There's 2 of them. So when we bring oxygen total to the table, that is a -2, and it neutralizes the potassium. So potassium has an oxidation state of +1. Oxygen has an oxidation state of -1. Okay. One more with you, so we can see how this charged ion works over here. All right, so we're doing D. So going through our list of rules, oxidation state of a free element. We don't have a free element. Oxidation state of a monoatomic ion, not a monoatomic ion. Sum of the oxidation states of a neutral molecule. Well, this is not a neutral molecule. It's a charged molecule. So in an ion, it's equal to the charge of that ion. So when I take this sum of sulfur plus the 4 oxygens, the sum of those numbers has to be a -2. So that's a very important rule. Next we go metals. We don't have any metals. Then we go to our non-metals. Here, we don't have any fluorines. We don't have any hydrogens, but we do have an oxygen. So we're going to establish that first. So the oxidation state for oxygen is a -2. So now we can go back to this rule now that we've established something, right? So oxygen is a -2, and there's 4 of them. So as a group, that brings a -8 to the table. So what is the oxidation state for sulfur? So that we have sulfur plus -8 equals -2, right? So the sum of these has to equal the charge. So the oxidation state for sulfur is a +6. So sulfur is +6. All 4 of my oxygens bring a -8 to the table. 6 plus -8 is -2. So that's how we use this hierarchy list to establish oxidation numbers. This is an important skill to have because what we're going to do in the next lecture is we're going to start looking at, okay, sulfur was a +6 as a reactant. Now it's a +4 as a product. Did it lose electrons? Did it gain electrons? So take some time to practice this assigning of oxidation numbers. And in the next lecture, we will start looking at how those numbers change. I hope you guys found this helpful.